Hi there! Welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jin Kim, and today we're going to delve deep into the electrifying world of electricity. Let's get started. We live in the modern age, where we are heavily reliant on electricity. It only takes a single power cut to remind us how helpless we can be without electricity. No light, no warmth, no refrigeration, no memes. Oh, the horror. I mean, even right this second, as you're listening to this podcast, you're actually hearing my voice that was encoded into electrical signals by my microphone, transported to you via cables and wireless networks, changed back into sound waves via your speakers or headphones, and played into your ears. Electricity is an incredibly useful form of energy that has allowed us to completely revolutionize how we live. We use it every single day, and yet, how many of us actually understand how it all works? Like, what actually happens when you turn on the light switch in that fraction of a second? Where is the power coming from? How does it create light? And how does the power company know how much to charge you for it? So, in today's episode, we're going to learn about what electricity is, the fascinating history of how we as humanity harness the power of lightning, what a power grid actually is, and much, much more. It's a lot to get through, so without further ado, let's explain to you how electricity turns on the light as if you're a child. How do you turn the light on at home? You probably have a switch or a button that you can press, and presto, you have instant light. The same goes for many convenient things. The toaster, the microwave, your TV, your heater. Everything seems to magically work at the push of a button. This magic is called electricity, and it would seem like magic to anyone living in the past. And we're not talking like ancient Egypt or Greece times, but merely 150 years ago. You can think of electricity as the food that machines and devices need to eat to be powered up. No food, no power, just like when you miss lunch. So, how does it work? First of all, for electricity to work, you need something called a circuit. Think of it as a ring of garden hose. Except in a circuit, we would normally use copper wires like the kind you see in cables. The ring is closed off as a loop, but it has two attachments. Obviously, it needs to be connected to a tap to provide the water to flow in the hose. This is the power source, whether it's a battery, the wall power outlet, or a potato. Next, it needs something that the water can work on, like a sprinkler. Because otherwise, what's the point? This attachment can be lots of different things in electrical circuits, such as a light bulb, a heating element like what toasters use, or even something as high-tech as a computer. Okay, we now have a circuit with a battery, wires, and a light bulb. Let's fire it up. When everything is connected up, the battery can feed the whole circuit with a stream of electricity particles called electrons. These electrons, like the water in the garden hose, will just flow from one end of the ring to the other. But they go way faster than water, like as fast as light. When the electrons get to the light bulb in like a nanosecond, the light bulb acts like a bit of a bully. It says, "Whoa, Eddie, you gotta slow down, buddy." It resists the electrons from getting past it, so the electrons have to fight a bit to push through. This means the electrons have to do some work, which gets the light bulb a bit hot and bothered, working up a sweat. And when metal wires get hot, they glow, like, those old school heaters you might have around the house. And this is exactly what happens in the filaments inside the light bulbs. Well, at least old kinds your parents are used to anyway. You have cooler light bulbs nowadays that use something called LEDs, which make light from electricity in a slightly different way. Anywho, one way or another, the electrons have to do work as they get past whatever is resisting them, and the resistor takes that work and changes it into heat, light, movement, or some other useful purpose. The electrons, all tired from their work, go back to the battery, and then a new set of electrons start their journey through the circuit from the other end, and the loop goes round and round while keeping the lights on. Once you know how circuits work, you can even adjust how much power the light bulb gets. You can turn the tap on stronger so the pressure builds, making the electrons run faster. This is called voltage. You can also make the hose bigger and wider so that more electrons can flow through in a given time. This is called current. So, there you go. Now you kind of understand how an electric circuit works and what terms like voltage and current mean. All you need to think about are garden hoses and water flowing. But what's this? Turns out electricity is way more complicated, and what I've told you isn't exactly true. Like the very important fact that electricity doesn't quote unquote flow in the same direction as the electrons are moving. It's the opposite way. Welcome back. Alright, we're in for a big one today. Electricity is a super deep and complicated topic, and there's no way we can cover all of the interesting facets of it nor the intricacies in a single podcast episode. That's what engineering and physics degrees are for. But what we can do is help you understand the basics of how electricity works, how electricity is provided to us, and some of the interesting history behind one of the most useful forms of energy in the modern world. But first things first, we need to talk about what electricity is before we even get to how it works. So for that, we're going to take a brief trip to the smallest object in the universe. Well, kind of. The atom. We've covered the atom a few times in the show, so we'll be brief this time. The atom is made up of three main things. There's the central nucleus, which is a positive bundle of protons and neutrons. But what we care about today is the third thing, zipping around in an orbit around the nucleus, the negatively charged electron. These electrons don't orbit the nucleus like the moon does the Earth, but they instead form a kind of a cloud shell, because you never know where the electron will be exactly, just the probability of where it might be. But that part's not important, that's all quantum physics nonsense. What we care about today are charges. Electrons are negatively charged, and protons are positively charged. This will come up a lot, minus and plus, negative and positive. And you definitely came across this concept if you've ever had to put batteries in a remote or a Game Boy or anything. Most batteries have a plus side and a minus side. When you have the same number of electrons as protons in an atom, the atom is neutral, as in it doesn't have any charge. But if there's an imbalance, like the atom has too many or too few electrons, it becomes charged. Too many electrons and the atom becomes negative, whereas too few electrons results in a positive atom. This is important because in the electricity world, opposites attract, likes repel. That means two positive atoms will be all ew, gross and run away from each other, whereas a positive atom and a negative atom will cling together like horny teenagers. Same goes for electrons. They kind of act like hipsters. They don't want to stay in a negative area full of other electrons. They want to be different and go to places that have fewer electrons, that are less negative, that are more hip. So if you create a circuit, a loop made out of stuff that electrons can travel easily through, and set up a negative end and a positive end, electrons will want to go from the negative to the positive side. And boom, that movement of electrons and shifting of charge is what we call electricity. You don't even need a circuit for electricity to be generated. Think of static electricity. You can build up a charge just with friction. If you take a glass rod and rub it repeatedly with a cloth, you'll find that teeny tiny things like dust and strings and hair suddenly get drawn to the glass rod because it's become charged. This is because the cloth stole some electrons from the glass rod, making both the rod and cloth charged in opposite ways. When the positive glass rod touches another negative thing, say you wearing a fleece jumper, then the electrons from your negative body go, "Ooh, hello sexy positive rod," and immediately jump ship to even out the charge. This is what we call discharging, and you feel it painfully as a shock. When it happens at a larger scale, such as water molecules in a thundercloud rubbing against each other to generate a charge, and the charge being so intense that it ionizes the air so that electrons can flood down and join the Earth, we call it lightning. And you can actually see the awesome amount of electricity zapping down. Another important thing to know is that electricity is one of the fundamental forces holding the universe together. In our previous episode on magnets, episode 39, we talked about electricity and magnetism are actually two sides of the same coin. Two different ways of the force called electromagnetism that can be expressed. If you haven't listened to that episode yet, don't worry, we'll cover a little bit more about electromagnetism in today's episode. But it's important to know because it highlights how important electricity is. Not just in powering our entire modern world, but actually running the universe. Heck, even light is a form of electromagnetic wave, so yeah, electricity is literally everywhere. And yet, given how fundamentally important it is and how we can find examples of it everywhere from light to lightning to static electricity, we've only truly harnessed the power of electricity in the last 150 to 200 years. Why is that? For this, we need to delve into the scientific history of electricity. As with so many other things on this podcast, the history of electricity goes all the way back to ancient Greece. A philosopher named Thales of Miletus discovered back in 600 BC that if he rubbed a piece of amber on fur, it would attract very light objects such as feathers and hair. It would even sometimes give you a shock, as in static electricity, that classic prank. Unfortunately, from here, there's a huge gap in the history of electricity, because even though people like Thales dabbled in studying electrical phenomenon, such as static electricity and lightning, no one properly studied it for a very long time. There are records of ancient Romans using electric fish to treat headaches and arthritis, and there are numerous mentions of electricity being used as parlor tricks such as giving people a shock or making your hair rise up all frizzy. But outside of that, electricity wasn't really known at all. It wasn't really until the 18th century that we made any headway into figuring out electricity. Around this time, many scientists started becoming intrigued at the properties of static electricity. Why was it that objects could become imbued with a property that could make it pull objects towards it or push others away? What was making objects attract and repel each other? To give Thales some credit, the scientists named these objects electrics because the Greek word for amber is electron. That's right, it all ties together, you see. Further research showed that you could divide objects that had become electric into two groups. If you took one object from column A and another from column B, they would attract each other. Opposites attract. If you take objects from the same column, then they'd repel each other and push each other away. That's right, scientists had figured out pluses and minuses, that some objects will gain more electrons with rubbing, whereas others will lose them. But they still didn't know why this happened. What was the magic power causing this phenomenon? Since the objects were electrics, they took the same principle as elastic bands and elasticity and named the power electricity. Now we're going to cover some important figures in the history of electricity, so pay attention. The first important figure we can't ignore is Benjamin Franklin. That's right, it's not a coincidence. It's the very same man that you find in the back of a $100 US dollar note, the founding father and American philosopher, Benjamin Franklin. Franklin was a bit of a jack of all trades, and science and invention was certainly two of his areas of interest. He was fascinated by electricity and did many experiments to try and understand it. For example, you've probably heard of the famous experiment where he flew a kite into the clouds of a thunderstorm, had a key dangling from the wet string, and felt the electric buzzing of the key, proving that lightning and static shocks were the same kind of force, electricity. But more importantly, Franklin actually coined many of the terms related to electricity that we use today. Have you ever wondered where the word charge comes from? Well, Franklin was a bit of a prankster, and he made some devices that could store electricity, like a rudimentary battery. He found that he could use these batteries to shock people, as the stored electricity jumped to the person it contacted. Franklin thought that an appropriate analogy for this phenomenon was like a rifle loading and charging, then firing or discharging, and that's why we use those terms for electricity. He also found that you could link a bunch of these devices together to increase the electric power. Kind of like how on a ship there's rows and rows of cannons that fire at the same time to devastating effect. What's that called again? Oh, that's right, a battery. But what Franklin is best known for in the field of electricity is that he figured out that something must be carrying electricity. Because this is the old days before atomic theory. Scientists typically thought that things were transmitted in fluids, like they thought light was carried in a fluid. So electricity must be carried by some kind of fluid as well that we can't see. If you rub cloth over a rod to charge it, there must be some kind of transfer of electric fluid. And the Earth must be a giant reservoir of this fluid, which is why touching the Earth negates electric charges, because electric fluids equilibrate quickly. This is what grounding is. So if you stand on a wax block, use friction to build up a charge, and touch an object with less charge than you, the electric fluid must jump from you to the other object to balance out the amount of electricity, hence the shock. All of this sounds remarkably similar to our current understanding of electricity, right? And this is back in the 1720s, more than 300 years ago. But there's one thing that Franklin got massively wrong. He thought that the electric fluid was positively charged, and it must flow from positively charged objects to negatively charged objects. Makes sense, right? Nope. As we've discussed, electricity is actually due to the movement of electrons, those negative little Nancys. Which means electricity is technically carried by a negative particle. But it wasn't until 1897 that J.J. Thomson discovered negatively charged electrons and named them in honor of those amber pieces Dallas experimented with. So scientists agreed to not reinvent the wheel and pretend that electric charges still go from positive to negative, even though the electrons are moving in the opposite direction. Because if there's one thing humanity does well, it's put arbitrary definitions on natural phenomena and put things into artificial boxes. This principle, that electricity flows from positive to negative and electrons are like salmon swimming up the stream of electricity, is what we call conventional current. And thankfully, it means that we didn't have to go back and find or replace all the pluses and minuses and reverse them. Electricity research really took off from here. In the 1780s, Luigi Galvani discovered that electricity affects animals because he noticed that you can make dismembered frog legs move with charged metal objects. Alessandro Volta took this principle and invented proper batteries, a device that could store electricity to discharge at a later time on command, letting scientists experiment with electricity freely. We'll come back to batteries later on in this episode. In 1820, Hans Christian Ørsted figured out that electricity and magnetism were related, because compasses would point towards copper wires with electricity running through them. He figured out that electric currents running through wires produce teeny tiny circles of magnetic fields, meaning electricity and magnetism are actually two sides of the same coin of the same force, electromagnetism. You can listen to episode 39 for more details on that. Following from here, the genius André-Marie Ampère built on Ørsted's law to figure out all the mathematical equations that could predict how electric currents and magnetic fields work, and came up with a whole set of laws and equations called electrodynamics. So, now we have the ability to use maths to calculate how electricity and magnetism behave, meaning we could invent other technologies using technology. For example, Michael Faraday was able to figure out the power of induction, that rapidly changing magnetic fields can produce electricity in nearby copper wires, basically the opposite of Ørsted's law. He used this discovery to create the first electric generator. Now, we could create electricity on demand as long as we had an energy source. Then, James Maxwell decidedly figured out the maths of induction, coming up with the famous Maxwell equations, a set of equations that we use to this day so that we can map and predict how electricity would behave in circuits and machinery, so that pretty much all of our electrified technology can work properly. He also figured out that light is actually made up of electromagnetic waves, so visible light, ultraviolet, infrared, microwaves, radio waves, X-rays, gamma rays, they're all actually forms of electricity. And I know, it's boring to listen to a list of white men discovering and naming things, but you have to understand, this is the power of mathematics. Just by discovering the right equations and formulas, we can now harness the power of electricity, taking it from the domain of scientific research and parlor tricks to actual usable technologies such as electric generators, lighting systems, and appliances. You'll often hear in science fiction stories how people are trying to crack maths problems such as the Riemann hypothesis to predict prime numbers and the P versus NP problem, and how solving these equations could completely revolutionize our technology. This is exactly how that would happen. Thanks to the works of people like Ampere and Maxwell, you're able to listen to my pre-recorded voice at any volume you want while driving in a car that travels much faster than a horse, to go home to a well-lit house with dinner cooked in an electric oven, things that people from 500 years ago couldn't even imagine. So yeah, the late 1800s is when electricity properly reached the regular Joe and Jane Block, with Thomas Edison conceiving and implementing the first power grid in Manhattan to electrify houses for the first time. And the age of electricity dawned, giving us the modern era. There's a lot more history to talk about, such as the War of the Currents and how Volta invented the first battery, but First, it's been a while, so let's take a break. And when we're back, we'll look at a super simple circuit and learn some elementary electricity physics. Welcome back. Already, just by covering the scientific history of electricity, we've learned a lot of new terms, like current, voltage, discharging batteries, induction, and so forth. Now that we know how humanity came to understand electricity and harness the power of lightning, let's take part and improve our understanding of how electricity works as well. The best way to explain how electricity works is by using a super basic circuit. A circuit can be as simple as an AA battery wired up to a single light bulb, or as complicated as a motherboard in your computer and phone, with hundreds of electric components all connected by some kind of conductor. By the way, we're going to learn a lot of terms, but in my defense, many of them will be familiar to you. For example, a conductor is any material that lets electricity run through it very easily, like metals and salty water. And since we know that electricity is all about electrons flowing in a direction, conductors must let electrons move pretty freely. Obviously, if we want to utilize electricity to power our devices, we want that electricity to travel from the power source to the destination as efficiently as possible, which is why we use copper wiring, a metal that is very conductive. But sometimes, we want to prevent electricity from passing go and collecting $200. So we use materials called insulators that protect you from electricity. These materials, such as rubber and air, don't let electrons flow freely, so they act in the opposite way to conductors. Alright, so let's start setting up a circuit. First, we need a power source. In our circuit, we'll be using batteries, devices that can store electrical charge and then discharge them if you connect the plus and minus ends with a conductor, such as copper wiring. We'll talk more about how batteries work in the next section, so be patient. If we were to take a piece of copper wire, make one end touch the plus end of our battery and the other end touch the minus end, then presto, we have a circuit. In this circuit, the negative end of the battery has a lot of negative charge, as in lots of free electrons. The positive end has much fewer electrons. As we talked about before, nature loves equilibrium. So the electrons in the minus end want to even out with the plus end. You know, like how people want to move out of congested, overpopulated cities and live in the empty countryside. In the battery, however, as we'll find out later, the two ends are separated, so the electrons can't fill the gap. But once the circuit is connected, they find that suddenly there's this new shiny coppery highway leading them from the busy electron-filled minus city to plus countryside. Metals like copper have all of the atoms arranged in a matrix, or 3D grid, like an apartment block. Because the atoms are all stably linked, they can share their electrons freely, like some kind of free love commune. That means that electrons can swim around the metals as much as they want, and that's why it's a conductor. So the electrons from the battery's minus end zip through the copper matrix wire, racing to the plus end of the battery. You can think of this another way by picturing water flowing down a hill. Imagine that you have a bucket of water at the top of the hill. If you were to pour it, the water will run down the hill because gravity, right? This is what's happening with electricity. It's the force of the electrons just wanting to even things out and chill out. But before we get further, we do need to clarify one thing. Remember how I said earlier that Benjamin Franklin defined conventional current in the opposite way to electron movement? This is where it gets relevant. Even though the electrons are flowing from the minus to the plus end of the battery through the circuit, we say the electricity is flowing from the plus to the minus end because tradition. Yeah, just roll with it. So from now on, whenever we talk about electricity flow directions, we're talking plus to minus. So the top of the mountain is the plus end, and the bottom is the minus end. You dig? Okay, with that out of the way, let's go a bit deeper and figure out what electricity is in this circuit. All of these electrons moving and charges shifting exerts a force. Even though each electron is teeny tiny, when there are a trillion of them, the overall force they exert can be pretty powerful. Now, a quick disclaimer. This topic has been one of the hardest to research in the history of this podcast because the physics of electricity gets really deep and full of maths at every level. Because this is a podcast aiming to explain complex concepts in simple ways, not Physics 101, I'm going to skip a lot of the maths equations, such as Coulomb's law and Poynting vectors and Maxwell's equations. Also, before the engineers and physicists give me the actually, we're gonna simplify things and just not talk about how electricity isn't actually about the flow of electrons, but electric field lines. Don't even start with me. Ugh. I'll link some awesome YouTube videos that explain these in far more detail in the show notes if you're interested in further learning. But for this episode, let's keep it as simple as possible and pretend that electricity flows. So, back to happy little flowing electrons pushing and exerting force as they race through a circuit. You can directly visualize this force with static electricity. Remember how opposites attract and like repel? This is the same force, the force of electric charge. And like any force, such as gravity, we can quantify how strong the force is with units. You've probably heard of the term voltage as a measure of how strong electricity is, like high voltage power lines and 9-volt batteries, etc. Voltage is how we quantify how much work the electric force can do. The higher the voltage, the more work you can do with electricity. This work might be how much the electricity can heat up an element to generate heat and light, or how hard it can spin a motor to drive a car. You can increase voltage by increasing the gap of electrons between the two ends of the batteries. The bigger the inequality of electrons, the greater the potential difference, which means greater voltage. In our water running down the hill analogy, this is the same as making the hill taller. You hopefully already know that the higher something falls from, the more energy it hits the ground with. So if the water is flowing down from a higher point in the hill, it will have more pressure and more power when it smacks you in the face. Another way to think of voltage is thinking of electricity in a circuit as a garden hose. If the hose is the copper wire and the water flowing through its electricity, voltage would be the water pressure. The higher the water pressure, the harder you can water blast and shoot water further, right? So, more voltage, more work. Conveniently, we measure voltage in volts, named after the scientist Volta who made the first proper batteries. On the topic of voltage, there's two other important aspects of electricity we need to discuss. First, there's current, which is how much charge is passing through the wire over a period of time. It's measured in amperes or amps. So if you ever see 5A on a charger, it's talking about the current. It's saying it's 5 amps. I always found the current super confusing. Like, voltage is easy to understand, it's just the strength of the electric charge. But what does current mean? In the garden hose analogy, current is basically how wide the garden hose's diameter is. The larger the garden hose, the more water can flow through it in a unit of time. This means that higher current chargers and cables can deliver more electricity per second. Lastly, we have resistance, measured in ohm. You'll notice that all three of these crucial values are named after scientists who were instrumental in deepening our understanding of electricity. After all, they say that the greatest honor a scientist can receive is having their surname used in lowercase. That's a little science joke for you fellow nerds out there. Resistance is basically how hard it is for electricity to flow through the circuit. The higher the resistance, the harder it is to flow. So less electricity makes it to the other end. It would be like clogging up the metaphorical garden hose with sand, or putting a filter in there to reduce the flow. Now, before we get back to the circuit, and I promise we're getting there, is that these three variables, voltage, current, and resistance, can be tied together with a beautiful, elegant equation known as Ohm's law. Ohm found that in a circuit, the voltage is equal to the current times the resistance. As in, if you have the same voltage coming from the same power source, you can increase resistance to decrease current, and vice versa. You can rearrange the equation to calculate any three of current, voltage, or resistance, as long as you know the value of the other two. Sorry, I said I won't get too mathematical, but Ohm's law is just so simple and elegant that I have to mention it. I mean, V equals IR, where I stands for current. It just sounds so clean, doesn't it? Ohm's law is also particularly useful in calculating one more unit, and I promise this is the final unit that you have to learn in this episode, the watt. Watt, also named after a scientist, is the measurement of power, or the amount of work a force can do. And by work, I mean how much energy something can exert over a period of time, like joules per second. Oops, there's another unit. Sorry for breaking my promise so early. We use watts to calculate power of all kinds, but you'll most commonly see it for noting how much electrical power you can generate or need to use. To calculate how much power an electric current can provide, all you need to do is solve the equation P equals IV. And yes, I know PIV means something very different in other contexts because I'm a doctor, but shh. So, power equals current times voltage. Easy as that. And because you know Ohm's law now, you can actually substitute in resistance instead of current or voltage. Once you solve this equation with some simple algebra, you end up with a certain amount of watts of electrical power. So, what does 1 watt of power actually mean? Well, for context, your smartphone needs about 0.1 watts, just 10% of a watt. To power a regular household, you need 1000 watts, or a kilowatt. This is why when you look at the power bill, you'll see that you're charged by the kilowatt, because that's how power companies know how much electricity you're using. If you want to power a small town, you need about 1 megawatt, or a million watts. A mid-sized city requires a gigawatt, or a billion watts, and to power the entire world, you need about 3 terawatts, or 3 trillion watts. Anyway, let's finally get back to our circuit. The two ends of the battery are connected by a conductive copper wire. Electrons travel from the minus end to the plus end, and electrical charge flows from plus to minus. All of this happens at the speed of light, which is why it looks like things happen instantly when you flick a switch on. Now, speaking of switches, they're basically a circuit component that either completes or disrupts a circuit. When a switch is on, the circuit is a complete ring, so the electrons can make the whole journey. But when a switch is off, you make a gap in the circuit, either by disconnecting the wires or by blocking the electricity with an insulator, and the electricity can no longer flow. Okay, so we've made a super basic circuit now with a battery, wires, and a switch. But this circuit is kind of useless. The electricity just flows, vibing and chilling, not doing anything useful. What's the point of learning about voltage and how much work electricity can do if we're just letting it spin around in a circuit? So let's put the electricity to use by introducing another circuit component, the resistor. A resistor, as the name suggests, is anything that resists the flow of electricity. We've already talked about how some objects let electricity flow through it super easily, like metals. But insulators don't let electricity through well. So resistance is basically the opposite of conductance. If you try to push electricity through an insulator with high resistance, it really wants to get to the other side. So it pushes and pushes and pushes, like trying to open a stuck door. As it does this, it exerts the electrical charge force we discussed before, voltage. This work can cause multiple things, but the most simple result is that it generates heat. This is how electric heaters and toasters work. We make electricity run through a metal coil with high resistance, forcing electricity to be converted into heat. And when you heat something up a lot, it tends to glow. You've probably seen those outdoor heaters glow red when they're on. This is electrical resistance manifest. And yes, the astute listener probably has figured out by now what this means. Old school light bulbs, or incandescent light bulbs, use the same principle to convert electricity into light. Light bulbs contain highly resistant tungsten filaments that are coiled up really tightly. So not only does the electricity have to push really hard to get through, but it has to keep pushing for a very long time. The end result is a lot of heat and light, which is why you should never ever touch a glowing light bulb if you want to keep your fingerprints. By the way, fluorescent lights, neon lights, LEDs, and lasers all produce light from electricity in very different ways from this, but we unfortunately don't have time to cover them today. Maybe in a future episode. Same with semiconductors and transistors. I mean, I finally learned how they work through all my research, but I think we best save that for a future episode when we talk about computers. Oh lord, you have no idea how much time I spent researching and deep learning various things about electricity for this episode. You're welcome. Anyway, like transistors and diodes, such as light-emitting diodes or LEDs, there are various kinds of components you can slot into a circuit to either change how the electricity flows or to make electricity do some work. But for today's episode, we'll just talk about one more electronic component, the capacitor. So far, we've talked about electricity as a constantly flowing energy. You can only have it stored in the form of a battery. When it's being used in a circuit, the electrons are zipping around at light speed, so once it's out of the bag, it has to be used right away in a resistor. Or it just returns to the battery, right? Well, turns out there's a special circuit component that lets us do something cooler. Capacitors are two metal plates, one negatively charged and one positively charged one, that are facing each other with a space in the middle. Because of these oppositely charged plates, called an electric dipole because there is a negative and positive side, we can store an electric charge in the middle of a circuit. What's cool about this is that so far, we've talked about voltage and current as a pretty constant thing. If you want more electric power, you need to ramp up the voltage to provide more juice. But a capacitor lets you save up electric charge for a rainy day. And by rainy day, I mean blowing a heap of energy in one go. For example, camera flashes need a massive burst of electrical energy to provide the bright light, but it only needs it discharged in one go. So instead of jacking up your camera to a massive battery, a capacitor lets you charge up the voltage, saving it up like a piggy bank, and then BAM! It breaks open the piggy bank and releases the charge all at once. The other place capacitors are really useful in are defibrillators. Same principle. The electric charge is stored up, then released as a powerful shock to help the heart beat in a regular rhythm. We can really talk on and on and on about how various circuit components work, how putting light bulbs in series or parallel affect the resistance of the circuit, and how transistors work as teeny tiny switches with no moving parts, but then we'd be here all day. Now that we have a basic understanding of how a circuit works, and what the words voltage, current, and resistance mean, let's move on to another important question. Where do we get all this electric power? How do batteries and power outlets work? But first, let's take a very short break again. Welcome back. First, let's talk about batteries. Batteries can come in all shapes and sizes, from tiny button batteries to heavy lithium-ion car batteries to literal mountains. That's right, you can turn a mountain into a battery with science. One of the most annoying things about electricity is that, except in the case of static electricity, it needs to flow to generate power. So before the days of the power grid and readily available electricity from wall outlets, scientists needed to figure out how to store electricity in a container. Like, you can't experiment with water if you have no cups or containers for it, right? You just slip in the puddle and hurt yourself. The first real battery was invented by an Italian scientist named Alessandro Volta, who we thank by naming the unit for voltage volts after. Volta was inspired by Luigi Galvani's discovery in the 1780s that when a charged metal instrument touched the dissected frog's legs, the legs would jump even though there was no body or head to control it. Galvani thought there must be some animal electricity that powered this, which was kind of perceptive in that living things do use electricity for nerves, but wrong in that it wasn't where the electricity was coming from. Volta thought that the electricity must be coming from the metal instead, so he set out with the following experiment. He took a zinc and copper plate, stacked them on top of each other, but with a cloth soaked in a salt solution between the two plates. That's what's called a voltaic cell. Then he took a bunch of these cells and stacked them on top of each other, forming what's called a voltaic pile. As we already know from our old friend Benjamin Franklin, you can increase the voltage of a battery by stacking them in series. You know, like how your torch needs 2 or 3 batteries lined up one by one. Anyway, let's look at just a single voltaic cell. Copper and zinc both react with the salt solution in the cloth, but in opposite ways. Zinc undergoes oxidization, where the zinc atoms give away electrons because they feel generous. This means that the zinc plates become negatively charged because it's generating free electrons. Copper, on the other hand, undergoes reduction, where the copper atoms want to take all the electrons they can get. This makes it positively charged because it's sucking up all the electrons from the area. So now we have a cell that has a positively charged end and a negatively charged end. Hooray! We have an electric dipole. If you were to take a conductor like a copper wire or frog legs and connect the two ends, the electrons suddenly have a path they can travel down from the negative to positive end, or minus to plus, and an electric current is generated. This is how batteries store charge, by making electrons on one end and removing them from the other end. As the electrons, and consequently the electric charge, flows from one end of the battery to the other, the electron count evens out, and eventually the battery loses the stored charge, aka a dead battery. We now have rechargeable batteries where you can use electricity to reoxidize and reduce the metals and re-establish the potential difference, which is pretty rad. Volta's voltaic pile is pretty much the foundation of how most modern batteries work. Nowadays, we use various different metals that can oxidize or reduce, such as lithium. And there are more and more technological advancements happening to make batteries more efficient, larger, cheaper, and safer. The really cool thing about Volta's battery is that it's actually inspired by something from nature. That's right, electric eels. There are many animals that can sense electric fields around them and use it to navigate or hunt prey, such as sharks. But there are only a handful of animals that can generate enough electricity to actually shock things around them. The electric eel is obviously the most famous, but there's also the electric catfish and electric rays. These animals have evolved to become living batteries, so that they can discharge up to 600 volts of electricity, stunning or killing other living things that they want to eat or just piss them off. If you look at an electric eel, you find that up to 80% of its body is made up of cells called electrocytes, not to be confused with electrolytes. If you look at these in cross-section, you notice something. They look a lot like voltaic piles. Electrocytes look like disks stacked on top of each other. The cells pump positively charged sodium and potassium ions out of the cell, so that the inside of the cell becomes negatively charged. If you want to learn a bit more about how cells become electrified using ion pumps, have a listen to episode 44 on electrolytes. Anyway, thanks to the ion pumps, the electrocytes can build up an electric charge, negative on the inside, positive on the outside. But this isn't helpful. We need to have a minus end and a positive end, not just all on the outside and inside. So what the electric eel can do is send a nerve impulse to the electrocytes, commanding them to discharge. When this signal hits the electrocytes, they open up ion channels so that the sodium and potassium ions flood back in. Now, we have an influx of positively charged particles. Although we've mostly talked about negatively charged electrons moving, electricity is actually just the movement of any charged particle, positive or negative. So all we need to do is make sure that the positive ions are moving only in one direction, and then we'll have an electric dipole and an electric current. The electrocyte cleverly does this by only opening ion channels on one side of the disk. So if you imagine the stack of disks, where the top is the head end and the bottom is the tail end, the electrocytes only open up ion channels on the tail end. This means that the positive charge floods in from tail to head, while more positive charge move from tail to head, because they're being pumped out from inside the cell to the head end of the stack. It's a bit hard to visualize, but essentially, you've created a circuit where you have positively charged particles all flowing in one direction, exerting electric force. But because there are no wires to direct that force, it radiates out from the eel's body like a blast, hitting everything around it. There's some contention about how much the eel feels the shock as well, but I digress. Anyway, Volta had studied the anatomy of electric eels, so he decided to do some old-fashioned pattern theft of nature that humanity is so adept at, and invented the voltaic piles to imitate them. One last thing about batteries, I mentioned that you can make mountain batteries. What the hell am I talking about? Well, remember that all a battery needs to do is store potential energy. For example, a compressed spring has a ton of potential energy, because if you let it go, it's going to spring out and push with a lot of kinetic energy. Same with objects that are very high up. They have gravitational potential energy, because as they fall, they'll accelerate with gravity. Mountain batteries use this principle to allow us to store massive amounts of energy. Basically, if you have a mountain with a large water reservoir at the top, then the stored water has a lot of potential energy. If you release the water down some channels and have generator turbines along it, the water will offload its potential energy by pushing the turbines, converting its stored energy into electricity. And if you need to store energy back into the battery, you use electricity to drive pumps that can pump the water back up the mountain into the reservoir. Simple as that. So, why do you need a giant battery like this? Are we powering the world's largest Duracell bunny, or are we just really paranoid that we're going to have a long blackout? Well, kind of. Let's wrap up this episode by talking about humanity's most complex and largest machinery and network, the power grid. Up until now, our hypothetical circuits have been set up with batteries. But batteries have a huge downside. They can only hold so much charge. Which is fine for small devices such as remote controls and the old school Game Boys, but if you want to power anything more, like a toaster or a fridge, you need a juicier, constant power supply. This would also let you use rechargeable batteries, such as those found in your phone and laptops and electric cars. And this is why most of your powerful electric appliances are connected to the wall outlet, where they can receive a continuous stream of power. But where's the power coming to feed that power outlet? Have you ever wondered how power gets to your house in the first place? This is where the power grid comes in. The power grid, technically called the Wide Area Interconnection, is the largest machine in the whole wide world, depending on your definition. It's arguably the most important as well, because turns out it's not love or laughter that makes the world go around nowadays, it's electricity. The power grid is a massive network of power plants that generate electricity and power cables to deliver said electricity to people that need to use it, which is most people. Unless you're truly off the grid and get all of your power from solar panels and fuel engine generators, you use and need the power grid to some degree, whether you're a residential household or a company or a factory. We'll get to how the power grid works, but first a little pub quiz question. Who invented the first power grid? Well, here's how we can tell apart the people who've been paying attention. Because I already told you that it was Thomas Edison, electrifying Manhattan with the help of brilliant scientists and engineers working for him at his company, and funding from JP Morgan. Edison, who was more of an entrepreneur than a scientist or inventor, saw the future potential of an electrical grid, a system where power plants would generate electricity, distribute it via power lines, and deliver it to households and businesses that would use new appliances running on electricity. Until this point in the 1870s, electricity wasn't really in demand. It was still cutting-edge technology that hadn't made much of a splash in normal day-to-day life. This was all about to change though, especially with Edison's company refining and tuning the incandescent light bulb and arc street lights to be safe and usable in residential spaces. Electricity was going to be the future. And he was right. But here's where things get interesting. Although Edison is credited as establishing the first power grid, his initial power grid had a huge problem. It was difficult to scale up in size. You see, up until this point, electric systems were usually powered by something called DC, direct current. All of our circuits that we've talked about so far today use DC. Electrons flow directly in one direction, and so does the charge. It's a very simple and easy to use electrical system, so much so that all of our batteries just use exactly the system. It's also much easier to use with electric motors back then, which were being developed around the same time. But the problem with DC is that it's hard to ramp up to really high voltages. The initial power grid worked with much lower voltage than what we're used to. It was also hard to transmit the electricity over long distances, as it would lose power the further it went through copper wires. In Edison's grid, DC electricity could only reach 1 mile, meaning you needed heaps of power plants placed every mile throughout Manhattan to effectively scale up the grid. Enter the competition, AC, or alternating current. Yes, that's right, that's where AC/DC gets its name from. Another American entrepreneur by the name of George Westinghouse decided to focus on an alternative electric system called alternating current, where the flow of electrons are reversed over and over. So, for example, modern AC grids have the electrons flow one way, then flip the direction to the opposite way, 60 times a second. This is why you see the 60 Hz frequency label on some electronic items. Due to the way electric field lines work, which we're not going to go into today because it'll do my head and your head in, even though the electron flow is flipping back and forth, the direction of electric charge is still in one direction. so you can still deliver power from the generator to the outlet. AC has some significant advantages over DC. Namely, you can jack up the voltage through the use of a device called a transformer, more than meets the eye, which amplifies the electricity. The higher voltage lets you transmit AC over tens and hundreds of kilometers, rather than a meager 1 to 2 kilometers that DC is capable of. It also means that you have less power loss as you transmit, so it's so much more efficient. Furthermore, Nikola Tesla, the great wizard of the West, invented the induction motor, which could use AC instead of DC, so DC was really losing the competition with not much to show for itself. Thomas Edison was not happy about this. He liked money and didn't want to see his DC-based empire crumble. So he set up some intense lobbying against AC, primarily claiming that AC was way less safe than DC. You see, there had already been some instances of linemen and drunk people getting accidentally electrocuted, being shocked to death by the high voltages running through the lines, going through their body, frying their heart, causing severe burns, and etc. Side note, this is a medical pedantry, but electrocution technically is only when you've been executed and killed by electricity. Electro for electricity, and cution as in execution. If you survive it, you've had an electric shock injury, not electrocuted. Similar with drowning, you've only drowned if you died. If you're still alive thanks to resuscitation, then you've had a near drowning event. Thanks for listening in to Dr. Jen's Medical Linguistic Pedantry Corner. Anyway, Edison really amped up his lobbying when the electric chair came around. People looked at all the cases of people shocking themselves to death by accident on power lines and thought, that might be an efficient and clean way to kill people on death row. Yeah, people. So they did tests on stray dogs and horses, eventually inventing a system that could literally electrocute a human being with a strong electric current. Edison pushed hard for the electric chair to use alternating current and Westinghouse's own generators to prove to people just how dangerous AC was. The first execution by electric chair ended up being a shocker though, pun intended. Turns out the 1000 volts that they used for this first shock wasn't enough to kill the poor inmate. The inmate was knocked unconscious, but his heart was still beating. So they quickly tried to double the voltage and shocked him again, but they kept having technical issue after issue, and the whole ordeal lasted 8 minutes, with the poor inmate undergoing seizures, burns, and eventually even catching fire, like in that scene from The Green Mile. Ugh, awful. Really not the clean, quick killing that they thought they were going to do. Anyway, despite Edison's best efforts to discredit AC, historically called the War of the Currents, the effectiveness, transmission distance, and significantly cheaper cost of using AC meant that it won out as the predominant electrical system in the end, and is the de facto electric current that all power grids around the world use now. So, back to the power grid. How does this awesome, gargantuan machine work? It all starts with a power source. As per the first law of thermodynamics, energy cannot be created or destroyed. It can only be converted from one form to another. So electricity must also be generated by converting it from another form of energy. Power plants do this primarily with steam turbines, giant machines where you boil water with a lot of heat, and the steam that is made from boiling pushes and spins turbines, which generate electricity through the magic property of electromagnetic induction. You see, the rotating blades are attached to a shaft that has magnets inside of them. Surrounding the magnet shaft is a stationary copper wire coil. Remember what happens when a magnet is turning in different directions in a metal coil? That's right, you generate electricity through induction. This is because as the magnetic fields change directions, the electrons in the wires get swirled around, kind of how the moon pushes and pulls on the Earth's oceans to create the tides. This electron movement creates an electric charge. It's exactly how the induction in your kitchen stovetop works as well. Power plants turn steam turbines using various fuel sources. The most common type is a coal plant that burns coal to release a lot of heat, boiling the water. You also have geothermal power plants that use the heat of the earth, hydroelectric dams that use flowing water to turn the turbines, wind turbines where wind spins gigantic rotary blades, and nuclear power plants, which uses nuclear fission of uranium or plutonium as an energy source, as we talked about in episode 55. And then there's solar panels as well, that use clever chemistry and physics to convert the kinetic and radiant energy of sunlight to electricity. But that's a whole nother topic as well. Alright, so we've made a lot of electricity. Let's get it to the people and light up their world. As we mentioned before, AC has the advantage of having the voltage raised considerably high through the use of transformers. These devices have a pair of coils. The second set of coils usually are wound tighter than the first, so you have many rounds of coils compared to the first set. Thanks to electrical magic, if you pass an electric current through the first set of coils, you can induce an electric current in the second set of coils, but the voltage increases proportionately. What this means is that if you have 5 coils in one set and 20 coils in the other, you get a 4-fold increase in voltage. These transformers are called step-up transformers, and they can bump up the voltage of the AC current from 10 to 25 kilovolts to 100 to 765 kilovolts. That's more than 100,000 volts, which is what the Pokédex says is the intensity of Pikachu's Thunderbolt. This super high voltage lets the power plant transmit electricity to houses hundreds of kilometers away. This happens through power lines, bundled cables that can transmit such high power electricity without shocking everything around them or melting. Power lines are suspended in the air using pylons, because the air around it acts as an insulator and actually helps keep the electrical transmission efficiency, much like the plastic coating around electric cables. Now, obviously we can't just feed 100,000 volts of electricity into your household straight into your laptop, so we need to transform it back to a lower voltage. There are various substations along the transmission route between the generators and your house that step down transform the voltage down to somewhere reasonable in the 110 to 240 volts range. In Aotearoa, New Zealand, our standard voltage is 230 volts at 50 Hz. That means the alternating current is flipping directions 50 times a second. When you plug in your device or appliance into the wall outlet and turn the switch on, you're essentially completing a really long circuit from your device to the power plant generators. Now, here's a fun fact. Most people think that they're tapping into some kind of electricity reservoir when they plug into the wall. But as we found out, electric currents can't really be stored. You can have batteries that store electric charge, but because we don't have cheap, high-capacity batteries yet, there's no way power plants can store that amount of electrical charge needed to keep a city running. This means that whenever you plug in and switch on, the electricity needed by the device is being generated by the power plant at that second. That's right, most of the electricity is made fresh on demand, like a Subway sandwich. So when you turn the device on with wall outlet charging, you're actually having electricity that used to be coal or uranium or wind like a second ago. Which means there's a huge problem with power grids. The power plants need to produce almost exactly the right amount of electricity that is needed at every given moment. But how? It's not like they're spying on every household to see when people are turning on their TVs and hairdryers and gaming PCs. So how can they know how much electricity is needed at any given moment? This is the classic demand versus supply issue of power grids. If power companies don't manage the supply of electricity well enough to match the demand, you can have brownouts, where you have random power cuts or overloads, where substations and transformers can blow up due to the excess power. So, power plants try to predict when the peak times are for people needing more electricity, such as in the morning when people get ready for work, or evenings when everyone's cooking on stovetops and using ovens, or turning on the heat. Depending on what the demand is, they can either crank up the generators to burn more coal or accelerate the nuclear fission of nuclear reactors, or shut down generators to prevent too much power being supplied. It's an extremely delicate operation that requires constant monitoring, maintenance, and fine-tuning to make sure that our happy electric world to keep rolling. Thanks to technology, power grids are getting better and better at regulating the demand and supply, with things like computer systems, load balancing, and voltage regulation. But something in the last few decades is upsetting the balance: renewable energy. We all know by now that fossil fuels are horrible for the environment, especially because of carbon dioxide emissions fueling climate change to dangerous, irreversible levels. So we've actually made a lot of progress in the last decade of shifting our fuel sources from fossil fuels to more renewable green sources such as solar power, wind power, and hydroelectric dams. There's also nuclear power, which is actually one of the cleanest and safest sources of electricity, pound for pound. But the problem with renewable power sources such as wind, sun, and water is that we can't control them easily. With coal, we can easily transport it and adjust the amount we're burning at a given moment to control the electricity supply. But you can't tell the sun or the wind to just cool it for a bit. They do what they want. So, if the supply is too much for the current demand, they might need to shut down generators, which can be very costly and slow to start back up. You also can't increase the power supply when you're facing a brownout, so you might need to fire up coal plants to supplement the supply. This is a major problem that we're facing currently. As our world becomes more and more modernized and electrified, our energy demands are skyrocketing. There's even a projection that we'll be needing triple the current energy supply just to meet the demand by 2050. And thanks to global efforts, we're relying less and less on fossil fuels, with some countries even running mostly on renewable energy sources. But since our existing power grids were designed with fossil fuels as the foundation, we need to come up with drastic new solutions to ensure that we can keep the lights on and avoid shutdowns and overloads. There are many exciting solutions. For example, more and more people are calling for the need of supergrids. Currently, power grids are massive and tend to cover sections of countries. But what if my neighborhood is producing too much power, and your neighborhood is needing more power to meet the demand? There's no way to share the power to even out the supply and demand. This is why people are suggesting that we need supergrids, power grids spanning entire countries or even continents. The more interconnected power grids are, the more you can redistribute excess power to areas that are facing higher demand or lower supply, meaning everyone is happy. But as we've seen from the recent invasion of Ukraine, politics gets in the way. Because countries don't like depending on other countries for their energy. It means they can extort you when things turn sour. Still, one can dream. The other possible intermediate solution, while we're revamping our grids, is inventing better ways to store massive amounts of electrical power so that we can save up electricity when we make too much and use it up when we need more. We're currently bottlenecked because we haven't found ways to make large, cheap, high-capacity batteries yet. Most rechargeable batteries use metals that can get quite expensive, so having massive battery farms to offset the power grid is just not cost-effective yet. But there's hope. There's continuous research in progress on making better and cheaper batteries, such as using iron and air as a way to store electrical charge in the form of rust, or the mountain batteries we mentioned before. If there's one thing humanity does well, it's solving problems. Thanks to brilliant, hardworking scientists and engineers and policymakers, we're constantly preparing for the future and the unique problems we face as we evolve as a species. Who knows? Maybe in 50 or 100 years, we'll live in a world where you can charge the device just with wireless power in the air, or literally any surface around you can act as an information hub and computer, like in the world of three-body problem. What an exciting future to look forward to. So, what did we learn today? We learned that electricity is a type of energy produced by the movement of charged particles, such as negative electrons. We learned that electricity and magnetism are two sides of the same coin, because they're actually the same force, linked by electromagnetism and induction. We learned about the fascinating history of how scientists discovered and came to understand electricity. We learned the meaning of many terms related to electricity, such as current, voltage, resistance, watts, and so forth. We learned about how circuits, batteries, and power grids work to provide us and our wonderful devices and appliances with unlimited power. Well, we learned there are limitations to this power, and that power grids need to work hard to match demand and supply, and how renewable energy sources are both helping us save the planet while causing headaches for power grids. Well, that's it for today. Thank you for listening to Explain This. We'll skip the 2-minute explain today because the script is now almost 11,000 words long, and we've easily broken the record for our longest episode yet. Hooray? Man, don't say I don't work hard to deliver you content. I've been getting some lovely positive feedback and comments lately from new listeners, so thank you to all the newcomers and old compatriots alike. Especially if you're spreading the word about this amateur podcast. Kudos to you, and I love you. Keep it up so we can get these rookie numbers up. I hope you've learned something interesting and maybe even useful today. We'll see you next time. Bye for now. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter.